In this video, we're going to talk about the leading term test. But before we can get to that test, let's talk about what the graph of f of x equals a times x to the n looks like. Now here a is just some constant and n is a positive integer. Okay, so for example, in the first case, f of x equals x squared, the a is 1 and the n is 2. Now notice this is a polynomial, but these are very simple polynomials. We're not adding or subtracting a bunch of terms. We just have one term here. Okay, now of course we know what f of x equals x squared looks like. It looks like this parabola. But actually any function that has the form ax to the n, where a is a positive number and n is even, will look something like this. For example, if you wanted to graph x to the fourth power, it looks very similar to x squared. It's not exactly the same. It's a little steeper over here. They cross each other. Okay, they cross each other at 1 comma 1 and minus 1 comma 1 and also 0 0. In fact, I've have a picture here. I found an online graphing calculator. In blue is the graph of x to the fourth power, and in red is the graph of x squared. Notice they look they have a similar shape, but they're not exactly the same. Now also, if you wanted to graph, for example, instead of x squared and x to the fourth, what about the graph of x squared and 5x squared? Okay, how do those look like each other? Notice x squared again is in red. 5x squared is just kind of stretched vertically. Okay, it's the same thing as x squared, only it's stretched vertically. Okay, but the point is any function that has the form ax to the n, where n is an even number, okay, 2, 4, 6, 8, so forth, and the coefficient is a positive number, it'll look like this. Now negative x squared, if you have a negative coefficient but an even degree, it'll be just the opposite. It looks upside down like this. Okay. Now x cubed, we have an odd degree polynomial. Again, the leading coefficient there is 1, but an odd degree polynomial, f of x equals x cubed, has this shape. X to the fifth would look very similar, not exactly the same, but very similar. And also negative x cubed looks like this. Okay, now here are some graphs of some more complicated polynomials, and let's see what we notice. Now first of all, this graph is negative x to the fourth minus 2x cubed plus x minus 1. We see the basic shape here. Okay, notice that's an even degree polynomial with a negative leading coefficient. So which graph does it kind of look like? Well, it looks kind of like negative x squared. It has that same shape. Now, it wiggles around here a little bit, but it starts down here and then it ends down here. Okay, it wiggles around a bit, but it looks very similar to negative x squared because the leading coefficient is negative and the degree is even. Now, if you have an even degree polynomial with a positive leading coefficient like this, it starts up here at the top and ends at the top. It wiggles around a little bit, but it starts at the top and ends at the top, just like x squared did and x to the fourth did. Okay, now for odd degree polynomials, notice they start and end at opposite places, right? This one starts up in the upper left corner and it ends in the lower right corner. When I say starts and ends, I mean it just keeps going up and up and up, and here it keeps going down, down, down. Okay, anytime you have an odd degree polynomial with a negative leading coefficient, it has that basic shape. It starts up here and then it might wiggle around some, but then it'll end down here, just like negative x cubed did. Okay, and if you have an odd degree polynomial with a positive leading coefficient, okay, the leading coefficient is 1/2 in this case, it has this basic shape. It starts down here, ends up here. So that's the basic content of what the leading term test says. It says the basic shape, or in other words, the end behavior of the graph of a polynomial is determined by the leading term. And more specifically, the leading term tells you the degree of the polynomial, and we're wondering, is the degree even or odd? And also the leading term contains the leading coefficient, and the question is the leading coefficient positive or negative? Okay, so what you really have are 4 cases. Okay, if you have an even degree polynomial with a positive leading coefficient, the basic shape of the graph looks like this. Now, in the middle of the graph, it's going to wiggle around some, but the ends of the graph, if you thought of them as arrows, they'd both be pointing up. Okay, even degree with negative leading coefficient, the arrows are both pointing down. Odd degree polynomials have the arrows pointing in opposite directions. Okay, odd degree with a positive leading coefficient looks like this. Kind of think of x cubed. The graph of x cubed looks like that. Okay, and an odd degree polynomial with a negative leading coefficient looks like this. Okay, now you might wonder, why is this the case? Well, let's take a look, for example, at the graph of part C here, negative x to the fifth plus 7x cubed plus 4. Why is it the case that if we go further and further to the right, the graph is going to go down, 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 keep going further and further down? Well, if we pick a pretty big number for x, okay, you could pick a big number like 100 or 1,000, but let's just take like 10. If we pick a big number for x, say like 10, is this going to be a positive number or a negative number? Well, if you do 10 cubed, you get 1,000. 7 times 1,000 is 7,000. That's pretty big. But if you do 10 to the fifth, it's much, much, much bigger. 10 to the fifth is 100,000. So you'd have negative 100,000 plus 7,000 plus 4. You'd have about negative 93,000. So if you're way over here at 10, it's going to be way, way down at negative 93,000. Because what happens is that first term, that leading term, overpowers all the other terms if you have big values of x. Okay, if you pick a really big positive or a really big negative value of x, this term is going to overpower all the other terms. And so the end behavior, now what matters in here, these terms will matter, but the overall shape of the graph is determined by that leading term. Okay, now let's do a quick example of matching. Let's match the graph with the function. So I've drawn some graphs of some functions, 4 graphs, A, B, C, and D, and I also have some formulas for functions. Now the first formula is negative x to the 6th plus 2x to the 5th minus 7x squared. Notice that that is an even degree polynomial with a negative leading coefficient. Okay, an even degree polynomial with a negative leading coefficient, the only one that could be would be this one, okay, part C. Okay, notice both arrows, if you thought of these as arrows, would be pointing down. Okay, the second one is an even degree polynomial with a positive leading coefficient. The only one that could be would be part B. Okay, in fact, you could graph these on a graphing calculator. If you do that, you have to make sure you zoom in the correct amount. You have the right viewing window. But if you do have the right viewing window, you can see the graph looks like this. Now, the third one, we have an odd degree polynomial with a positive leading coefficient, right? It's a coefficient of 1. So odd degree polynomials with positive leading coefficients, remember what those look like. Those look like this shape. Okay, odd degree positive leading coefficient. So which of these has that shape? Well, it's part D. Okay, well, it's not hard to determine what the last one is now. It's going to be A, but let's check. Is it really A? Well, we have an odd degree with a negative leading coefficient, and notice that has this basic shape, right? According to the leading term test, odd degree with negative leading coefficient should look like this basic shape, and that's what we have in part A.